Was asking about follow along with the chapter. But I'm like, well, how do you know what's going on? You're assuming chapter. And then, so then yesterday, the data files, blah, blah, blah.
Did I ask you guys anything about attendance? I keep telling it to ask you guys. It's not doing it.
I'm not getting a prompt.
It's not doing anything here, I don't think. Let's see how we're doing. Not at home. You guys are missing someone.
Somebody somewhere is friends with somebody who's in the Monday, Wednesday class, and maybe they were talking about it.
That's possible.
Because I noted Lisa in my class. She's not doing this. Yeah, that was
I just don't want to go
Whoa, this is due tomorrow?
That's right.
What?
Ethan, that's who I'm missing.
No, unfortunately, I left my laptop here at school last night. So I'm gonna have to like, right, oh no, I left it in class. And then the teacher just pulled it and held it for me. So I was able to go get it this morning, but
I didn't keep it.
like really choke through the last two. Luckily, I had all but the last two done, so I could probably just get home and really work on those.
See if I can save this.
I'm not very sorry. I'm trying to work.
Not to lose it.
But I'm sure it's good.
How's everybody doing this morning?
Good.
Good. Yay. On this second week here. Ready for a 3-day weekend? Did all of the chapter 1 stuff go okay? I haven't double checked to make sure everybody got all that done. It's due tonight, so you might not have it done yet. That's okay. But let me know if you run into any trouble with it or anything. We're going to start on our second chapter. We were working with a OneNote document. Let's not forget, let's get that open.
Oh, OneNote.
And I don't have any very good notes in my chapter 1 presentation. I'm sure you guys have better because I was just talking away. So I'm going to create a chapter 2 tab. So in OneNote, I just click the plus up here to create a new tab in my Trapper Keeper. Make this be chapter 2. And then again, I'm just going to load the PowerPoint. So I'm going to download it. Lesson 2, PowerPoint. And then drag and drop it into my OneNote. Maybe. And remember, we want to say insert printout to get that whole PowerPoint loaded into our OneNote document. Sorry, it's not letting me. There we go. just wonder, don't you? Looking at this pretty colored chapter or textbook cover, it looks like it's going to be all colorized and have some good illustrations, but I'm not seeing as many as I was hoping for. There's a bunch in the exercises and things, so we might have to supplement on our own. So this chapter, we're talking about data models. And let's look at our objectives really quickly here. We want to understand why data modeling is an important process and why the resulting data models are so important to us. How do we create a data model? There are some certain steps that we want to take. We're going to talk about business rules, what they are, and how important they are when we're making our data models. And we're going to understand a little bit about how evolutionary data models have come about, because there has been kind of an evolution. And we want to look at some alternative data models and the needs they fulfill, because you guys have different options available. And we're going to look at a little bit at how data models can be classified by their level of abstraction. In this chapter, our activities at the end in the Cengage stuff are going to be probably the majority of our activities, and they're good. They're going to make us really think about some of these data modeling characteristics. Okay, let me get this thing open right instead of looking at it that way. Hope everybody's been feeling good. Still feeling like it's real strong. I am. I get that cough, you know. And the other day I was coughing leaving here. I think Jackie knows all the cleaning stuff. And I did have a few people turn and stare at me. It's okay, really. I promise it's allergies. But you can tell if something is different. So we've got our objectives and we're looking at data models. Now, what is a data model? Well, I said we're going to have to supplement the illustrations in our book a little bit. Let's do that. I went to Google and I just searched for data model and went to images just to get some ideas. What are they talking about here? Are we going to get to use some Legos or some Play-Doh to build these models? No, we don't. We just do it all online. So our models are just a pictorial representation of our data, you know, the entities that we have in our data and the relationships between the different entities. So this one I clicked on here, it doesn't have any deeper meaning or anything. It was just real colorful, so I clicked on it. But it just shows that we have some sort of database that is geared off employees, right? I see that entity right in the middle. So I think, well, that must be important. And I see how employees are related to other things. So that's a really good data model. This one is just kind of an entity relationship diagram. We can have lots of different types. I can look at some of these others that aren't so colorful. Let's see what this one is. It just says it's a physical data model, and it shows that I have students and some sort of enrollment. So just from looking at the names of the entities, the squares in this data model, I can kind of get an idea of what this system is about, what's contained in this database. And that's what we want from pictures, right? We want pictures that give us an idea of what's going on without us having to do a lot of deeper reading, deeper research. And that's what a data model is for, to give us kind of a pictorial overview of our entities and their relationships. So really important, because we can use our data model to define these complex structures that exist in the real world of how our data is related. We can also use it as kind of an abstract way to document these objects and events that happen. So we can have it be really abstract, or we could have it be realistic. So depending on what our needs are. So we just can't get away from how important the data model is. That's one reason we actually went to this new textbook, because in our old textbook, it did a great job of functionally teaching you guys how to access the database, but it didn't do anything very much for teaching us the importance of the relationship of our data and how all of that, those relationships exist and make it meaningful for us when we're doing queries. So we just can't get away from how important it is. When we're looking at a data model, it's easy to communicate what's going on there. We can all see there's an employee, there's a product, whatever the entity is that we're mostly concerned about. Plus, it gives us a lot of different views of the database instead of just looking at an Excel spreadsheet or something like that that shows us the data. We can use that data model for our database administrators. They know what kind of database they need to create. Our software developers can use that model to understand how they access the data and how it's related to other data. And our end users can use that model to say, oh, where in the world could I find the price for a given item? So when we have a good data model, we're going to have a better database. When we're looking at each of the entities in our data model, I'm going to go back to that Google search result here. I'm going to bring up this colored one again just because it's really bright. We can see that each of the rectangles has a name, and that's the name of the entity that this model is describing. So if I look at this employee entity here, I see that it has some different data elements associated with it, like employee number. What else does it have? Division number, the first name of the employee, the last name of the employee, all things that are related to the employee. Each of those items, those data elements, are the attributes of that entity. And remember, I'm from north of Chicago, so I say attribute. Other people might say attribute. You might hear it said a lot of different ways. That's okay. That's a word that can be said a lot of different ways. Now, besides having all of the attributes or characteristics of that entity, all of the data elements that go with it, we want our data model to show the relationships that entity has to any other. We can have three major types of relationships. We can have one-to-many is a relationship, many-to-many, and one-to-one. We're going to talk about these relationship types a lot, and we'll get into it a little bit deeper in the next chapter. But when we're looking at our data in our data model, the way that we can identify what type of relationship we have is by thinking about that relationship. So for us here in this classroom, one relationship that exists is instructor to student. That's a one-to-many relationship, right? Because there's one instructor, many students, right? So one-to-many. Now, if I were looking at the instructor overall, or instructor pool in all of the CIS classes that we have available, that would be a many-to-many relationship. We have many classes and we have many instructors. Each instructor could teach many different classes. Each class could be taught by many different instructors. So that kind of complicated relationship like that is called many-to-many. Now, when we're looking at a data model, we're going to see it illustrated with some sort of connotation like this, M:(n) or M:(m) or star dot dot star. So the relationship is actually going to be illustrated in some data models with this nomenclature. What about a one-to-one relationship? Can you think of an example of a one-to-one relationship? We could have many of them. One that I would think of right away that we see a lot in different data models would be a person and their home address, right? Usually that's a one-to-one relationship. We might have a situation where it's not. They might have more than one address, but it's usually one-to-one. How about a person and their cell phone number? Again, we usually would think of that as a one-to-one relationship. You can see though, those relationship lines can get a little bit blurry. But a lot of times we'll say the most ideal one-to-one relationship we could illustrate would be a person and their social security number, right? Because we should have one person, one social security number. We know sometimes that's not the way it is, but that's how it's supposed to be. Now, those kinds of rules can be enforced in the database. And we do that by adding a constraint. A constraint is something that says, in the relationship between instructors and students, we must have one instructor or we can't have any students. So that would be a constraint. Another constraint I might have would be I only allow one home address per person.
So, on the data model,
Uh-huh.
does it usually say the relationship? Because I'm looking at one right now for airports, and then some of the connecting lines will say one, or will have an asterisk.
Uh-huh.
Is that representing the
It
relationship
could
they're
be,
having?
and such a good question. So many different ways of doing data model could evolve that we'll see some that do something one way. Some data models will show this relationship by the type of arrowhead that's between the different entities. Some data models will actually show this 1:1, like in parentheses beside the relationship. So we'll see a lot of different ways of doing it. Some data models don't put it in at all. So we'll see. But we want to get to the point where when we look at a data model, our mind automatically determines what type of relationship there is. Because we would look at that data model and say, oh, for one instructor, there could be many students. And so internally, we'll be thinking that as we look at that data model ourselves. So good question. So constraints can be something that we make manually in the database, or they can be kind of automatic. If we've already said we can only have one home address for one employee, obviously we have to have an employee before we can have their home address saved. So those kinds of rules are constraints, things that we have to live with, rules that exist. Now, another constraint could be something like our zip code. You know, if they're in Springfield, they can only have these certain zip codes. So we can have data constraints too. Okay, so a lot of these constraints can come from the rules of our business. So if I'm doing business in Springfield or I'm working with customers in Springfield, one of the data constraints or my business rules might be people have to have a valid Springfield zip code. I'm not going to let my workers travel outside the boundaries of Springfield. So that business rule could be something that I can add into my database. I can say, as I'm designing it, I'm limited to these specific areas. Business rules are those sorts of things that the business has decided, this is important to us, this is how we're going to do things. So whenever I'm working with business rules, I want to be really, really quick and to the point, right? As brief and precise as I can be. If I'm sitting in a meeting and all of the higher ups and everybody involved are talking about our new system, and I'm working to develop a data model, I'm going to be paying very close attention to the things that I talk about that are rules for our business's operation. And I'm going to try to get them all documented. I could also look through the policies and procedures of the company that are written, and I could use some of those to glean more business rules. But I want this list of rules. It's kind of like, I don't know, kind of like my atlas to say, you know, I can't do this. I can't violate that. Let's think of some. If I were, let's see, if I were a pharmacy, one rule I would have would be that the date on a prescription has to be today or before today, right? So I wouldn't take a prescription that was written next week. I would think that that was a sign of some sort of problem, right? So that would be one of my business rules. I could put that in when people are entering that data. I would make sure that that date on the prescription was today or before. Those kinds of things need to be documented. And we're gonna make that list as we're working with our business and making our model. Lots of places we can go to find these rules. Our managers, as I said in meetings, are gonna be just talking about some of the rules. They might make a list for you of specific things. Policymakers, if we're working with an organization, we might have department managers. We could have written documents and interviews with end users. We have some companies here in town that do a lot of hiring of different people. And one, well, like, let's see, like if you worked at O'Reilly's, you know, you're gonna know that a lot of your business rules are gonna have to do with car parts, right? With making car parts or remanufacturing them or whatever. I think they remanufacture them, selling them, moving them from one place to another. These are the kinds of things that we're gonna see as our business rules. What about if we go to work at Jack Henry? At Jack Henry and we're in the software world and we're selling to banks. Well, we're gonna have some really different policies and procedures and business rules than what O'Reilly's has, aren't we? We're gonna have real specific rules about what we can do if we're inside of a bank, you know, all those kinds of different things. So your business rules are gonna really be impacted by the type of business your company is doing, as well as where it's doing that business. We want to look at all these rules because we want to make sure that we understand how our company views the data. If I am working for one organization, like I'm working at O'Reilly's, how many times I sell this given part might be very, very important. That might be something that the management is really, really interested in. Where if I'm working at Jack Henry, maybe the things that they're really, really interested in are how many problem calls are we getting from our new software? Are we having specific areas of concern where we've got bugs or something? So we can think about how the important data to the company is different based on their rules. As we write our rules, we want to be thinking about how we can help communication between our different departments. Again, is our software department creating buggy code and our help desk is having to deal with it? At Jack Henry, is there a problem with this new release? How can we facilitate those two departments' communication? Now, lastly, we want these business rules to really help our designers, the people that are making this data model, designing our applications. How can we make them understand the role of all of our data, the scope of it, how important it is, what are our processes? We're thinking about changing the way the whole company works, maybe with the new database implementation. So we need to be very sure that everybody's understanding all the business rules involved. So those are our business rules. Questions about that? Can anybody think of any interesting business rules? I know there are some, kind of early. We have a bunch of new ones here lately, don't we? A bunch of new processes and things. So all of those are going to have an impact on systems as we move forward. We'll see stuff like that. A year or so ago, I guess a couple years ago, I mentioned that one business rule that was changing, or one constraint, is what's allowable in the sex field, right? Because it's always been like a male or a female. And then a few years ago, they started saying, well, there's also the option of other. And so that's fine to say out loud, but what kind of impact does that have on systems? What kind of impact does that have on the constraints that have been put in place? And then last year, one of the guys came from O'Reilly and said, well, you had to say it. We're working on a big project to update that field in all of our systems to allow for a third option. So when we build those kind of constraints in those business rules, to us, it might just be a simple thing at the time, but on down the road, the more flexible we can make it, the easier it's going to be to update on down the road. So developers 10 years ago did not think that that would be something that would change, right? So it wasn't something that was written that way. So all of those are constraints that we have to be concerned with. Now, looking at our business rules, this really helps us because when we're looking at our business rules, we're going to see the terms that are used by our company. Those nouns, those terms are going to become our entities, right? So if I'm working at Jack Henry, I'm not even sure what they call a bank. Some of them might call it a customer, they might call it a location, but that's really important. You know, we wouldn't want to create that entity in the database using the incorrect term. So the term that they use is the term that we're going to use in the database. One company might use customers, another company might use the term partners or affiliates. Those things are important to that company. So we have to make sure that those nouns, that verbiage is translated into their data model. In the same way, besides the naming our entities, that verbiage is going to help us understand the relationships. Because I could say things like banks have locations, right? Then that helps me understand that relationship. That if I'm going to document my customer's information, I'm going to know that a given bank could have many different locations. Besides just telling me how things are related, those business rules can tell me what kind of relationship qualifications there are and if things are bidirectional. There's one that's like that. There was one on this list here. Yep, here it is. We have one here in this really pretty data model. My employee here, has all these relationships, and notice a lot of them are not documented. This is not like a super good data model, right? Because a lot of the lines are just, you figure it out. There's a relationship here. But up here, there's this line here. Whoops. I swear that thing never works when I want it to. Sometimes it does. But here, it went to the website. It's all right. So here with our employee, I have this line that almost looks like a loop in a flow chart, right? And it points right back to the employee. And it says the employee supervises or is manager of. So if we knew what was going on inside of this data model, we would know that that means I can actually look at employees and somehow I can determine a list of employees that this employee supervises. And I would also be able to determine a list that this employee is manager of, which seems like the same thing. So there is a recursive type relationship within that employee table. So we have an interesting relationship going on there. Can have one employee supervise many others. So we'll look more at relationships like that as we go, but we can have some bidirectional relationships like that. So bidirectional relationships, entity A is dependent on entity B, but entity B is dependent on entity A. So what are we looking for? Well, in looking at all of these business rules and everything, we're trying to build this data model. What are the important entities for our company? You know, we've got to try to figure this out. Is a customer the most important entity? Is it a bank? What are we working with? And then we're going to come up with our names for our major entities. That's a really big deal because we're coming up with entities that people are going to use in this database for many years to come. So we need to make sure we're being descriptive of our objects in our business environment, and we're using terminology that's familiar to the users. This is a database, so The users may actually write their own queries and access the database directly. So we want to make sure it's friendly. When we're naming our attributes, our columns, our fields, we want to be descriptive of the data. And we want to make sure that we're always using proper naming. Some companies like to add a prefix or a suffix to their table name and use that prefix or suffix on all of the attributes in that table. So we have lots and lots of different options for naming. Our company could have naming standards. But no matter what we do, if we name things properly, we're going to have good communication between all of the people that are involved in this database. And it's going to be self-documented, which is really helpful. So earlier databases were set up as a hierarchical system. So that's kind of like a tree structure, kind of like our Windows file system structure. It's a hierarchical structure. We start at the root, like of our C drive, and we have folders, and within those folders we have folders, and we can keep growing that tree. Well, that hierarchical database model is that same kind of relationship, an upside down tree, where we would start at the top might be our company, and then underneath that we might have employees and things like that. Whenever we're working with a hierarchical model, we only have one-to-many relationships. Everything above is a parent, everything below is a child, and we can only have that parent-child type relationship. So we don't really have room for a lot of dynamic relationships. Let's go to Google and search. I'm going to search for a hierarchical data model. So you've seen them all the time. It's kind of like a class diagram, right? Classes related to each other. Here's a good one. Here's a hierarchical model. We have animals at the top, and under that we have fish and mammals. And under fish we have marine fish and freshwater fish. And so we keep just working our way down with our parent-child relationship until we've got down to the lowest level of detail that we need. So that's a hierarchical model. Top down, we're very used to it. We see that all the time. So we can only have one-to-many relationships there. So then another type of data model that we might encounter is the network model. And the network model is created, as they say, to represent complex data relationships effectively. So our first model, our hierarchical, just only gave us kind of that parent-child type relationship. A network model expanded things a little bit. It let a given entity have more than one parent. So let's search for some visuals of that. So much better. Network data model. So here we see the kind of complexity that we need that we couldn't have with the just straight hierarchical model. Look at our order. Our order is related to the customer that made the order. It's also related to the manager that dealt with the customer. It's also related to the salesman that dealt with the customer. So our order here has a bunch of other entities that are involved in it, if that makes sense. So our network data model lets us add that complexity instead of it just being kind of a one-to-one relationship. They even say standard concepts from this network model are still used by modern data models. So we see a schema and a subschema in these kind of relationships. The schema defines the entire database, the entire schema, the schema of things, right? And the subschema defines a small subsection of a database. So if I'm looking at a schema being my entire company, my entire organization, the subschema might just be the accounts payable department stuff. And we'll be learning later in the semester DML, data manipulation language, which allows us to add data into our database tables, delete data from our tables, and DDL, data definition language, which is the language that we use to create tables and database entities. So these concepts are still in use. And lastly, the model that we're using in our SQL course that we'll be looking at is the relational model. So relational is kind of takes the best of everything, and it says I want to base my data model on the relationships. The relationships of the tables are really important to me, and what's important is where my different rows and columns intersect in those relationships. So let's look at a model for that. That's what we've seen earlier. So I'll search for relational. And it is a lot like what I was finding just searching for data model. But if you notice, I'm finding like more specific ones. Here's a nice one. And looking at this one that has to do with students and courses and teachers, we have a lot of additional information supplied on this data model besides just the entities. So we're seeing some things about relationships and stuff like that. We'd have to really do a little of investigating and spend some time looking at it to determine what all it was showing us and what those different things mean. But we can see the relational structure allows us to get away from this parent-child relationship kind of at all. So instead of having parents and children in our relational database model, we have more peers. You know, everything is more related at the same level, and we can make connections amongst those peers and look at our data. So relational is more based on the relationships between our data. Now we have a lot of new types too, and our textbook will bring those up. So the relational database model has been around since about the 80s. This is what we're seeing with our biggest installed base. If we get out in the world, we're going to see more instances of relational database management systems than any of the others. And when we're working with a relational database management system, we add an R to that DBMS acronym. So instead of just database management system, it is a relational database management system. And that's what most of the ones that we'd be working with are. Network database systems are out there. So we were kidding around last time talking about old COBOL systems. Old COBOL systems would use those network model type database management systems. Some of them would actually use relational database models also. So we could see either one of them. But there's something that are still out there, and you'll get the opportunity to see. Whenever we're working with a relational database, we want to make sure that the user doesn't really have to do a lot of worrying about all that data. Here's a relational diagram, a real simple one. So for this agent entity, I have a bunch of properties, right, a bunch of attributes. We have an agent code. In looking at that diagram, there's a little key icon right beside the agent code. That means that the agent code is a unique identifier, and we won't ever see two agents in our database with the same agent code. They will always be unique. So that key tells us that that's a unique key for our agent table. Now, as I look at this diagram, I see a customer also, and in my customer table or entity, again, I have some attributes, and it looks like the customer code is the thing that's a unique key for my customer. Notice the prefixing of all of the property names in this model. Our agent entity has all of their properties prefixed with the word agent. Our customer entity has all of its properties prefixed with CUS, except the agent code. So we can see that there's a relationship between these two entities based on the agent code. So I should be able to take this agent code in my customer entity and find the associated agent in my agent entity. So what do you think about those prefixes? Do you like a prefix in front of all of those entity names? Prefix?
Helps kind of separate them.
It's nice. Would you like a suffix instead? Which would be better?
That'd be a little bit harder to tell from just looking at it.
It also be harder to sort.
It wouldn't sort right if it was a suffix. Is there any benefits to it being a suffix? There is. The benefits would be that we could find all of our area codes that they would sort together. So it's, again, 6 of one, half a dozen of the other. But the prefix is very, very helpful. And we'll see that a lot. We just want to make sure it's short because we don't want it taking up all of our screen space when we're looking at drop-down lists of our attributes. So beautiful. This is a beautiful relationship. So the thing about relational databases is that relational databases were conceptized, or that's not a word at all, but they were visualized and envisioned, and Dodd wrote his textbook or book about them because of SQL. SQL stands for Structured Query Language. And Structured Query Language, I've mentioned already, is the same across all different relational database management platforms. So if I know SQL, I can use it for Microsoft Access, I can use it for SQL Server, I can use it for DB2 on the mainframe with my COBOL programs. I can use that same structured query language. So SQL itself, the language, is considered an end user interface. Users are supposed to learn it. Users are supposed to be able to use it to query the data in their organization, help their management. SQL lets us query the data by looking at our entities as a collection of tables stored in the database. So we've been looking at these data models. If you think about them as each of their own table out in a database, I would be able to get information from my customer table and get information from my order table. There is an SQL engine that's included with relational database management systems to execute these queries and figure out what we want and return us results. When we look at our models, there's so many different ways that we can model our data. We've seen a bunch of different ones. They won't all be on the test, don't worry, you're not gonna have to be able to identify which type is which because they've evolved and there is no specific standard for data models. It's all kind of, this would be nice, this would be nice. So we can look at the examples out there and decide what's important to us. But what is kind of standardized is the fact that an entity relationship diagram, or ERD, is the model of choice for giving us a graphic visualization of our database. I'm going to let you get those couple of terms put in. We've talked about attributes a couple of times. Remember, attributes are the data elements for our entity. So at the top level, we have an entity, and then the entity has attributes. That entity also has relationships to other entities, and those relationships determine its connectivity. So here's some conventions, some notations, a bunch of different ways to make data models. First of all, the Chen notation. I've not used this one a lot. I don't have a lot of real world experience with the Chen notation, so we can experiment with it together. But what we have with Chen is this diamond representing the relationship between two entities. Okay, so these Chen diagrams can get really full of stuff really fast, right? Because instead of just having our rectangles to show entities, which can get very full, now we have to add this other symbol in for our relationship. But if we're really focused on relationships, if we're at that point of our design, then the Venn diagram is perfect because it's giving us the relationship. So I can say my relationship. I can look at this and say, painter paints painting, right? So it's establishing that relationship. One painter paints many paintings. So I can see how that relationship is established. It's a one-to-many relationship. What about this next one? I have employees and a skill, and the relationship between them is learn. So I could say many employees learn many skills, right? So I have a many-to-many relationship there. How about this bottom one? Here I have an entity employee and an entity store, and our relationship is manages. So one employee manages one store. So you guys can see how that would be in your database, and then all of a sudden you get that call that says, Joe's gonna manage 2 stores now. Yep, that messes things up. So we always have to be concerned about those kinds of things. But we can handle it. Okay, so that's Chen. We have a diamond for our relationships. Crow's foot notation. In a crow's foot notation, we're using the symbol at the end of the line to denote the relationship. So here we have one painter with those 2 hash lines that are right beside the symbol indicates one, paints many paintings. And the many is the foot heading into that entity. And here's our many-to-many relationship with employee and skills. And then our one-to-one relationship, one employee manages one store. Okay, so that's crow's foot. Now UML is the one that we've usually been pulling up when we're looking at Google, because these UML class diagrams kind of are a little easier to look at. We don't have quite as much busyness going on. In a UML diagram though, we're kind of left up to the person who made this diagram as to how they do it. And it's really hard to see there on the screen, so I'll look over here. Here we're gonna say one on one side, one-to-one, one painter paints. But on the other side of our relationship, we actually document that a painting is painted by one painter. So notice how that UML notation allows us to document both sides of the relationship, right? Because one mother may have many children and one child may have many mothers, right? So we have to be able to support the relationship from both sides. So that's what the UML class diagram gives us. Questions about those? You see the differences between the 3. You can see how easy it is to kind of mix them up, put different pieces together depending on what you need. But those are the identifying names for the different types of diagrams. We know from our programming classes that object orientation is very important and really adds to flexibility. So one thing that we would see coming down the pipes would be an object-oriented data management system where we could just define objects in their relationships. So an object-oriented data model, kind of our goal, right? That's what we would like to be able to achieve. An OO DBMS. I'm going to leave this up here for you guys to get in your notes, or just to highlight in the PowerPoint, because most of these should be terms you're familiar with. When we create a class model using Visual Studio, we're getting close to a UML model. Not quite. The UML model, using the Unified Modeling Language, actually has very specific rules about how we create that class diagram. And honestly, our textbooks kind of vary in their implementation of it. So we could go look at the UML if we wanted to get the exact specific rules on creating a class model. But that's what UML is our class hierarchy model. So we can see how closely they're related. When I'm looking at my entity relationship, my ERD for my database over here, and here is my software development UML class diagram that came from that. They're very close to each other. That's what we want. Sometimes we would like to just skip steps and be able to have our ER model become our UML class diagram, and we have tools and things that allow us to massage that data a little bit and transfer things back and forth. But that's where we want to be. So the extended relational data model supports object-oriented features. And then another option that a lot of people have implemented are XML files. And you've seen XML files where we have data that's tagged, and those XML tags define what each attribute is. The XML tags also define what entities we're working with. So we can use XML as kind of an object-oriented database. Other data models that are important to us and emerging right now are big data and NoSQL. Big data has a goal to figure out a way to manage huge quantities of data to provide high performance at reasonable cost. So for this one, you can think of Twister. If you've ever seen the movie Twister, my son is a meteorologist, so of course I've had to see it like 7 billion times. But in Twister, you know, Dorothy starts getting data and the computer starts going, and we're getting reams and reams of information from all of those sensors immediately. What do we do with all that data? That's a lot of data. And so big data is a big new field, and there are lots and lots of job opportunities for people that are specializing in how to handle that scientific data. That's the one where some of them are going back to the mainframes and using old mainframes to do their number crunching. So it's interesting. So when we're working with big data, we have a whole bunch of it. We have a huge, large volume. Our velocity, as I mentioned, like with Dorothy, it could be happening very, very quickly. It's very fast. And it could be a very large variety of data, right, from multiple sensors and multiple locations. So what is that, the 3 V's of big data? Volume, velocity, and variety. It's a huge amount of data coming at you very, very quickly. and we want to figure out a way to manage it and handle it. Because there is so many readings that are so similar to each other, they don't work well with our conventional structures. They don't have good, unique identifying keys. It's just data that is kind of expensive for us to store. So it's not very structured. It doesn't really give us, bless you, doesn't work well with our existing structures. So we have some new technologies that are available. Let's look at what is it OOP? If I look up, I'm not exactly sure how to say it. We'll do the dictionary.com thing and have it say the word for it. Hadoop. But this is a software library that's been published by Apache. So it's a library of functions that work well with efficiently storing and processing huge data sets. So that's an up and coming technology. Hadoop. And the associated distributed file system that goes along with it, again from Apache. MapReduce is another one. Let's check it. What is it?
Did we learn how to do Apache in this process?
Nope. Those are new emerging fields that are just coming out. So you'll have the tools available to you to do the research for those kinds of things. And that would be what you would want to put on your resume. You know, that I've researched the Hadoop tools and I'm interested in exploring those options and things like that. Because when you're working with emergent technologies like that, that's what the people in hiring positions are going to be looking for, is someone that even knows what it means, right? Because it's all just starting out. So that's what you want, any sort of research that you could do. MapReduce, let's see what it says. Processing and generating big data sets with clustering. So MapReduce would be one where we'll see people that have hundreds of PCs side by side, all connected via fiber, and they're doing clustering to try and number crunch those huge quantities of data. So how cool, there's new things out there, always new stuff available. And then NoSQL is, let's look, if I say it, I won't say it as well as Google would. What is So of course, MongoDB is one of the NoSQL database implementations that's pretty popular. You'll see it a lot. So it's non-tabular, stores data differently. So these are new, again, new meaning that they've been available for 5 or 10 years, kind of new in the field. And these are things that you can explore even further. We're going to get our solid foundation in relational data models and working with SQL, so that you can veer off into these new up and coming specialties really easily. So why would I want to do NoSQL? Distributed databases where I have multiple locations in many, many different places. Sometimes our relational database model requires a lot of data copying from one location to another to keep its structure intact, whereas these NoSQL databases can get away from some of that requirement. So they're really scalable, and I can make them available all the time, and they can handle errors and recovery from those errors a little bit better than relational database models. We're geared towards performance rather than transaction consistency. What does that mean? Well, a transaction for a normal or an older database means from beginning to end, I got a process completed. So a transaction for me, one thing that I consider a transaction would be going and getting gas in my car, right? I put my debit card in, I give it my PIN, if it's that kind. I fill up with gas, and then I put the gas pump thing back. Well, I'm used to doing that. That's a normal transaction. And I assume that if something went wrong, I would not get charged, right? So if I put my card in, I put my PIN in, everything's good, and there's some sort of failure with the pump, that transaction didn't complete, right? I shouldn't get charged anything. So we're used to transactions being handled properly that way. If our transaction fails, we don't get charged. Everything gets rolled back out of the database like nothing ever happened. So that's transaction processing. And that's the way relational database management systems were designed to work. We were worried at that time about transactions. Now, we're not so worried about transactions when we're looking at NoSQL and huge, giant, massive quantities of data. Instead, we're worried about how can I make this happen really, really fast? How can I crunch through all of these millions of rows of data and get information out really quickly? So we have different objectives. We might see as time goes by that different database management systems are used for different purposes because they have different objectives.
Am I understanding the transaction consistency right? Because in my head, it means translates to loss of data or loss of something. Is that what that's saying? Performance over transaction consistency?
Yes, that we want to make sure that we don't lose data. So if that, say I put my card in and the real transaction issue is where the facility maybe takes, what do? They take like $20 or $25 out of your card as like a just in case kind of thing. And then if your transaction is actually less than that, they refund that to you and all of that. So if your transaction fails, you would like that money back. So our database management systems are designed to be able to handle things like that and say, oh, this transaction failed, I'm going to roll it back. The data would still be maintained. It would just be that it has updated your back.
That's an example of consistency, right?
Mm-hmm.
So that, and that's what I'm trying to think of is, I guess I'm just trying to think, what would it, at what point would it be good? I don't mean to open a can of worms.
To me, I guess it's easier to think of that rollback of transactions if you're doing an online transaction. So say you're buying something on Amazon and you're already at the checkout and Amazon already has all your credit card information and you're trying to check out and you have some sort of network failure. At that point, that's unexpected, right? That network failure is not something that would normally occur. But the transaction mechanisms of the database management system that's in place and the application should know to not go ahead and continue to charge you for that data. They will leave it sitting so that next time you come to Amazon, it's all sitting there still in your shopping cart. They didn't go ahead and complete that transaction without you.
Right.
And that's important. We would like them to not do that.
But my question is so if the NoSQL databases are geared toward performance rather than that consistency, and I guess my question is, I'm trying to think of a time where the speed would be better than the mutations that you might get out.
Oh, okay, I see. So the speed would be better if I am a meteorologist and I need to query through the last 24 hours of sensor data to come up with a forecast. Because if my process fails, no big deal. I wasn't updating anything. I just need to read that data as fast as I can. So we're looking at that different kind of objective of just crunching that data, trying to come up with some sort of projection or something that won't matter that much if it fails. But yes, you're exactly right. It could fail easier and it might not have that capability built in to be able to recover. And as a database administrator or somebody that's working on a software development project, that's a really important question to ask, because you could be in a situation where you're working with your whole team, you're deciding, you're making these decisions, and somebody says, just out of the blue, I think we should use NoSQL. I've heard that that's the way to go. That's the newest database We don't want to be stuck with these old relational things. People say things like that all the time with no basis in fact. And then as a developer, you would want to investigate those things and say, is this really going to give us the transaction, base that we need, or is it going to leave us hanging somewhere because it's designed more for speed of data and not transaction processing? So those are exactly the things we would need to be concerned about. So here's our timeline. In the 60s, hierarchical databases, way back, really old. 70s, they developed relational. It wasn't until closer to the 80s that we really started seeing these entity relational type database systems. Since the 80s and 90s, we've been talking about object-oriented. Still don't really see a lot of OO-RDMSs. And now we have the NoSQL or NoSQL options available. So look at you, there's a lot of places where you can make some money making a new database management system that's better than all the rest. I think we're going to take a look at some of our labs here. Let's stop this and we'll come back to it next time. Let's go look at what we've got in our Cengage stuff for today. I'm going to Module 2 and the Apply section, and I'm going to start on the problems. And last time, since we hadn't done any before, I kind of led everybody through. Let's do that with this first one. And then I'm going to leave it to you and your study groups to talk about and go through the rest of these. Now, as you do this, as we split up, remember it's really important for you to talk about this with your study group. This summer was the first time I had an opportunity to teach this class online over the summer. And when we're looking at half the time, there's twice the work. And the teams, the groups that worked with their group, that talked things out and actually worked together, did so much better than the groups that didn't work together, because the database stuff is full of things that you might not realize on your own, little teeny gotcha things that you might not see, that working together with your group, someone else can say, oh, well, did you notice how this thing, this XYZ thing over here to the side could have an impact? And then you're like, oh, that changes the whole way that we should have done this whole thing. So I just can't emphasize to you how important it is to talk things out with your group. So let's look at this first one. Write the business rules that govern the relationship between agent and customer. Now, with business rules, we could get very, very specific with what's required. There are books, textbooks that are written on how to write business rules. So we could go from very, very casual to very, very specific with really extreme requirements. For ours, let's just try to get the basics down so that we understand what rules here we're encountering. Now, tell me, when I look at these two entities, what rule comes to your head first?
One agent for one customer.
Is that correct? We only have one customer per agent?
No, there's two that have
Yeah, what he said.
different codes.
Okay.
Like the agent code repeats for all multiple customers.
Yep, there's some. So our one agent could have many customers. So that's one rule. What else?
No agent has the same customer as a different agent.
Oh, okay. So how could we say that? A customer can only have one agent. Is that right? To try to simplify that rule. What else?
Each agent has a different code.
Say it louder for me.
Each agent has a different code.
Okay. Agent code is unique among agents.
Each customer has their own code.
Okay. Customer code is unique among customers. Good. What else? I'm looking for a really important one here. Could I have a customer that doesn't have an agent assigned? No. So customer must have an agent. Now, we could get really specific with all sorts of business rules here, but we would start just killing trees and things with all of our reams and reams of rules. Because we could say, you know, last name must begin with an uppercase letter. First name must begin with an uppercase letter. Middle initial must only be one character, must start with an uppercase letter. All those kinds of rules. All of those could be considered business rules. But we want to keep track of these really high-level entity type rules, because that last name rule could apply to every name that we have in our database, not just this entity. Mm-hmm.
I think each agent has to view the same area code as a customer too.
That looks like a really big rule. Agent.
And so if you look to like agents with the area code is 615, I believe are assigned to customers with the same area code.
It looks like that's a rule. So we could say agent serves customers only in their area code or in the same area code. You know, what's a clearest way to say that? It's kind of like when you're sending emails and you know you can be misinterpreted. Do what?
There's one on there that's got the 713. And
Is there one?
then agent number is 503. It looks
Oh,
like.
yep.
So close. It's like right in the middle. That 713 goes to 503, 503.
Oh, yep. They messed it up down there. You know, I almost wonder, looking at this display, I'd almost say, we just don't know, because it almost looks like Jackie's rule is valid, and there's a mistake in the data here. We don't know, is the data correct or is that rule correct? So we would have to put some sort of caveat on that one.
Or it could just be like borderline.
Yeah, it could just be a coincidence. You know, it might not have anything to do with any rules at all. It could be on the border, that there's more to that rule. So this is a really important one, because now we know that there are questions about that specific information. Does that matter? Was it just a coincidence? But definitely something we need to ask our users to get more information about, to find out.
I wonder if that's gonna be a question that pops up following the rest of the thing. Like, can you find any anomalies or any mistakes, any data, like, mistakes?
That would be a good one. Okay, so we're gonna do this tick my work thing, and it's gonna say that we're gonna grade it automatically. All right, so now for 2 through 17, and I don't think that you're gonna get through all of those today, but let's get started and see how much progress we make. As I said, I want you to work with your study group about those. You have many different options on how you work together. You could each try to answer it on your own and then compare answers. That would be a really good way, because we're just getting started. You could look at it first and discuss it and then come up with your answer all together. That might be a little, that might take a little longer than each of you doing it on your own, but it might come out to work better in the end. So whatever works best for you and your group. You guys as third members online, so you should be good. Everybody else everybody else has all their numbers. Okay, let me know if you run into any questions. I'm gonna try to find your last one to grade, see if I can find it.
I guess that's what you're doing right now.
Yeah. If I can find him.
They haven't given us a tool like I could do it. I guess you just copy one.
Oh, yeah, that's a question.
You have to like draw it out, or like. Yeah, like I know what it looks like, but like I thought I could use Excel for it, and I realized probably not.
Just make sure to have that style it wants. And what's close to it.
So if you want this stuff, for the lines, just right.
Oh, I was just really hard to see.
Like that? Like this, maybe?
I haven't figured out, I just want that. I don't.
Yeah.
He's off now. And I don't see him on Zoom.
Yeah.
He kind of dropped, I noticed like, I think when you stop.
Yeah, I don't think he's feeling very well, so I'll give him one. Because I don't want him to worry if he's not feeling up to it, but
There.
if he is,
So, I just inserted one that looks on.
Oh, I got a line.